Hi everyone, in today's session I am going to solve some of the numericals on steady flow energy equation. Let me just glance once what is a general form of steady flow energy equation which is applied to an open system. Basically the equation consisting of the energy in is equal to energy out, which is written as U1 plus P1 V1 plus V1 square by 2 plus Z into Z1 plus Q is equal to W plus U2 plus P2 V2 plus V2 square by 2 plus Z into Z2. U1 plus P1 V1 can be replaced as H1, and similarly U2 plus P2 V2 can be replaced as H2. The equation can be rearranged in terms of Q minus W as delta H delta V square by 2 and delta Z into Z2. Sometimes it can be written on mass basis. In place of Q I am writing Q dot, in place of M I am writing M dot. Similarly Ws dot and M dot. And in my last video I told mass 1 M1 is equal to M2, which can be written as rho A into V, which is nothing but rho 1 A1 V1 is equal to rho 2 A2 V2. So here rho is density, A is cross sectional area and V is velocity, accordingly at the inlet as well as outlet. Now let us take one example. 12 kg of a fluid per minute goes through a reversible steady flow process. The properties of fluids at the inlet are P1 is 1.4 bar, density 1, that is at the inlet 25 kg per meter cube, velocity V1 120 meter per second, U1 internal energy 920 kilojoules per kg, and at the exit the corresponding values are P2 5.6 bar, rho 2 5 kg per meter cube, V2 180 meter per second, U2 720 kilojoules per kg. During the passage, the fluid rejects 60 kilojoules per second and rises through 60 meter. Determine the change in enthalpy and work done during the process. So as to begin the problem, first let us write what are the inlet properties and what are the exit properties. So as it is given P1 rho 1 is nothing but it is indirectly I can get specific volume. So density is reciprocal of specific volume V1 and U1. Similarly, he has given P2, rho 2, V2 and U2. In the problem he mentions the fluid rejects 60 kilojoules per second of heat. So that has to be taken as negative. Q is equal to minus 60 kilojoules per second or kilowatt. Also in the problem it was mentioned that the fluid rises through 60 meter. Suppose if the inlet is at taken as reference and outlet as above 60 meter, the difference of Z2 minus Z1 in the problem is 60 meters. So basically this 60 meter is nothing but difference in elevation. Now let us just find out first what is the change in enthalpy so that I can substitute all the terms in the equation. So as you know, H is equal to U plus PV. So delta H is equal to H2 minus H1. So accordingly I am rewriting this as U2 minus U1 plus P2 V2 minus P1 V1. So here in the problem U2 is given, U1 is given, but both are kilojoules per kg. Here pressure is in bar, I am converting into kilopascal. So if you just check the given condition here, so 5.6 bar is converted as 5.6 kilopascal. So hence it is 5.6 into 100. Since V2 is reciprocal of 1 by rho 1, this 1 by 5 is nothing but specific volume indirectly as given as density. Is nothing but 1 by rho 1. Similarly, this is P1 1.4 into 100 kilopascal and this is 1 by 25, this is 1 by rho 1, so that the units balances. This is in kilojoules per kg, and this is also kilojoules per kg. So total delta H is 93.6 kilojoules per kg. Per kg is missing here, please note that. Similarly, I can have delta Ke, that is change in potential energy terms. So when I substitute V2 square minus V1 square by 2, I am getting as joules, and we have to divide it by 1000 so that it is in kilojoules per kg, because already delta H are taken in kilojoules per kg. After calculating all the values, so now we are left with delta potential energy, change in potential energy. Z2 minus Z1 is given in the problem as 60 into 9.81, which is in joules per kg, divided by 1000 makes it kilojoules per kg. By substituting all the values in the equation 1, that is Q dot minus W dot is equal to m dot into change in enthalpy H2 minus H1, change in kinetic energy V2 square minus V1 square by 2, and change in potential energy term, that is Z2 minus Z1. Since the mass given is in kg per minute, should convert into kg per second by dividing by 60, so that I can get the work or the power as minus 43.2 kilowatts. So here the negative sign indicates it is work done on the fluid or work done on the system, hence it is a power consuming device, like it may be a compressor or pump. Let us look into the another problem. The another problem is as follows. In a turbine of gas unit, the gases flow through a turbine at the rate of 17 kg per second, and power developed by the turbine is 14,000 kilowatts. So now here he has given the mass rate and he has given the power in terms of kilowatts. The enthalpies of the gases at the inlet and outlet are given. So this is H1 and this is H2 respectively. The velocities of the gases at the inlet and outlet, V1 and V2 is also given. Calculate the rate at which the heat is rejected from the turbine. So that means how much of heat is lost from this turbine during the process. Also asking what is the area of the inlet pipe. Given the specific volume of the gases at the inlet is 0.5 meter cube per kg. So let me just write the given data. Mass rate is 17 kg per second. Specific volume at the inlet is 0.45 meter cube per kg. Since in this problem he has given power, so what I will do, just I am converting power in terms of work. It's very simple. When I say power, it is nothing but joules per second or kilojoules per second. Now if I want to convert it as kilojoules per kg, it is nothing but total power output per unit mass. So it is nothing but kilojoules per second upon kilojoules per the mass is in kg per second. So what happens here? The second get cancels. So work done you are getting in kilojoules. And in the problem he has given H1, H2, velocity at the inlet and velocity at the outlet. We have the steady flow energy equation on unit mass flow rate basis by taking as Q minus W, small q minus small w has change in enthalpy, change in potential energy and change in kinetic energy. So now from the given data I can calculate change in kinetic energy. I have the values of V2 and V1. So similar to the previous problem, first I am getting in joules per kg, converting it into kilojoules per kg, and delta H has to be substituted and we have to get the value. Since there is no information about Z1 and Z2, delta potential energy term becomes 0. So when I substitute delta Ke, delta H and small w, which was small w, which was calculated in the previous slide. So Q has to be calculated. This is small w, kilojoules per kg. And this is delta H. Delta PE is 0 and this is delta KE. So I am getting the rate of heat rejected. Actually, it is not rate of heat rejected, just heat rejected as minus 7.02 kilojoules per kg. So since mass is given in the problem as 17 kg per second, I can calculate rate of heat rejected as 119.34 kilowatt. To calculate area at the inlet, I have the equation of mass as rho 1 A1 and V1. So since specific volume is given, so density is nothing but 1 by V1 A1 into V1. So by substituting the mass, by substituting the specific volume and velocity at the inlet, I am getting area as 0.142 meter square. The students are advised to work the other problems, and most of the problems will be having the similar type of approach. So please understand what is the given data, what exactly you are supposed to find out, and take care of the units while substitution and get the correct answers.